This is what happens when the most powerful telescope ever built looks back to the beginning of time and finds things that shouldn't exist. Galaxies as massive as the Milky Way blazing brilliantly when the universe was barely 300 million years old. Black holes billions of times heavier than our sun already fully formed in an infant cosmos. And chemical signatures that suggest stars had been burning for hundreds of millions of years before they should have even ignited. The James Webb Space Telescope has shattered every expectation we had about the early universe, and what it's revealing doesn't just challenge our theories, it threatens to rewrite the entire story of cosmic history. Scientists are scrambling to explain observations that, according to our best models, represent an impossibility, and some are starting to whisper what was once unthinkable. Maybe the universe is far older than we ever imagined, or maybe our fundamental understanding of how it all began is simply wrong. If you're ready to see how one telescope is dismantling a century of cosmology, hit that like button and subscribe, because what comes next will change everything you thought you knew about the cosmos. The year 2022 marked the beginning of something extraordinary and deeply unsettling for astronomers worldwide, when NASA's James Webb Space Telescope opened its infrared eyes and gazed deeper into cosmic history than any instrument had before. Scientists expected to find small, faint primitive galaxies in the earliest epochs, the cosmic equivalent of newborns just learning to crawl. But what they discovered instead was more like finding Olympic athletes competing in a marathon before anyone had learned to walk. The telescope revealed fully formed galaxies, massive and mature, existing at times when the universe was so young that according to every theoretical model, these structures simply should not have been there. Rohan Naidu at Harvard was working late one night in July 2022 when his algorithm flagged something in the early JWST data that made him call his girlfriend over immediately, because he'd found a galaxy that appeared to be inexplicably massive and dated back to just 300 million years after the Big Bang, making it older than any galaxy ever seen before. His words captured what would become the defining sentiment of JWST's first year, that this might be the most distant starlight humans had ever witnessed, but the discovery came with a problem that grew more troubling with each subsequent observation. This galaxy wasn't just distant, it was enormous, bearing a mass of stars equivalent to 1 billion suns, which was just a few hundred times less than that of the Milky Way's entire stellar population, despite our own galaxy being billions of years more mature. The record didn't last long, and in the following days and weeks, dozens of galaxy candidates sprang into view from various JWST surveys, with estimated redshifts reaching as high as 20, meaning they existed just 180 million years after the Big Bang, and some displayed disk-like structures that cosmologists had never expected to see manifest so early in cosmic history. Tommaso Tre at UCLA, leading one of the major survey teams, watched these discoveries accumulate and described what they were witnessing as galaxies forming stars like crazy, appearing as giant balls of star formation and nothing else, which was beyond their most optimistic expectations for what the telescope might reveal. By late 2024 and into 2025, the telescope had identified JD's Z140, a galaxy existing just 290 million years after the Big Bang, when the universe was a mere 2% of its current 13.8 billion year age, and this object held the distance record until researchers discovered an even more remote system they nicknamed MOM Z14, for Mother of All Early Galaxies, which pushed the boundary back to 280 million years after the Big Bang. Kevin Hainline at the University of Arizona, who regularly observes galaxies from billions of years ago because it takes that long for their light to reach us, found himself tracking one further back into the universe's history than anyone had managed before. And what made this discovery particularly shocking was that the galaxy appeared abnormally large and unusually shaped for such an early time. Brant Robertson at UC Santa Cruz, co-leading the JD's team that made many of these discoveries, called the findings completely unanticipated and likely to be seen as the most significant extragalactic discovery with JWST to date, because the observations demonstrated the immediate impact new telescope data could have on our knowledge of the distant universe. The problem was that these weren't just surprising discoveries, they were incompatible with the existing framework that cosmologists had spent decades building and testing. Michael Boylan Colchin at the University of Texas captured the crisis succinctly when he explained that even if you took everything available to form stars and snapped your fingers instantaneously, you still wouldn't be able to get galaxies that big that early, which meant this represented a real revolution in understanding. The James Webb Space Telescope, positioned 1.5 million kilometers from Earth and chilled close to absolute zero by its tennis court-sized sunshade, had been built specifically to revolutionize our understanding of the universe by uncovering details of cosmic dawn never before observed. This scarcely probed era, no more than a few 100 million years after the Big Bang itself, represents the period when the very first stars and galaxies coalesced, and how exactly this process unfolded depends on exotic physics ranging from the uncertain influences of dark matter and dark energy to the poorly understood feedbacks between starlight, gas, and dust. Glimpsing galaxies from cosmic dawn with JWST allows cosmologists to test their knowledge of all these underlying phenomena, either confirming the validity of their best consensus models or revealing gaps in understanding that could herald fundamental shifts in our comprehension of reality itself. What nobody expected was for the gaps to appear so immediately and so dramatically, because within months of beginning operations, JWST had found not just one or two anomalous objects, but dozens, then hundreds of galaxies that defied explanation. Rachel Somerville at the Flatiron Institute watched as galaxies exploded out of the woodwork, appearing in numbers that were tens, hundreds, maybe even 1,000 times greater than astronomers had anticipated finding in the early universe. Garth Illingworth at UC Santa Cruz, who had spent decades studying galaxy formation, stated bluntly that what they were seeing was way outside the box of what models were predicting, which meant either the observations were somehow fundamentally misunderstood, or the theoretical framework guiding cosmology for the past generation needed serious revision. The most troubling aspect wasn't just that these galaxies existed, it was that they appeared so mature and well developed at times when the universe should have been filled only with small clumps of gas slowly condensing under gravity. Young stars in general shine bright blue as they burn through their nuclear fuel rapidly, but with aged stars develop a redder glow as they cool down, and what JWST was revealing in these ancient galaxies were populations of old red stars that shouldn't have had time to form, let alone age. Joel Leger at Penn State explained that they had specific expectations for the type of galaxies living in the early universe, namely that they should be young and small, and previous studies with Hubble and other instruments tended to find small blue baby galaxies at early times, objects which had just recently formed out of the primordial cosmic soup and were themselves building their first stars and structures. Looking into the deep field images JWST produced, astronomers found instead what appeared to be reddish dots that, when analysed, revealed themselves to be galaxies bearing masses of stars equivalent to several billion times that of our Sun, with some individual galaxies possibly containing as many stars as the present-day Milky Way, but packed into regions 30 times more compact. The most massive galaxies in the sample were estimated to have masses just 2 to 4 times lower than that of our own galaxy, when the universe was only 3% of its current age, which was astounding and deeply problematic. Ivo Labey at Swinburne University, lead researcher on one of the major studies documenting these findings, described the galaxies as having somehow fast-tracked to maturity, and nobody could explain how that acceleration occurred within the known laws of physics. Emma Chapman at the University of Nottingham, though not involved in the research directly, recognised immediately what these findings implied for our conception of cosmic history, noting that the discovery of such massive galaxies so soon after the Big Bang suggested that the Dark Ages may not have been so dark after all, and that the universe may have been awash with star formation far earlier than anyone had thought possible. The revelation that massive galaxy formation began extremely early in the history of the universe upended what many scientists had thought was settled science, because the standard narrative held that galaxies formed from small clouds of stars and dust that gradually increased in size over billions of years, with matter coming together slowly in the early universe before eventually building up into the grand structures we observe today. That narrative couldn't account for the massive size of the newly identified objects, and astronomers were forced to confront an uncomfortable question that went to the heart of modern cosmology. If the telescope was finding too massive galaxies too early in the universe, as Alison Kirkpatrick at the University of Kansas succinctly put it, then something fundamental about our understanding of how the cosmos evolved needed to change. The discovery wasn't just about pushing back the timeline for when galaxies formed, it was about recognizing that the entire process happened faster, more efficiently, and under conditions that current theory couldn't adequately explain, which meant that either some crucial piece of physics was missing from our models, or the observations themselves required reinterpretation in ways that hadn't yet been discovered. Understanding why these discoveries are so revolutionary requires grasping how astronomers measure distances across cosmic time, because looking at distant galaxies isn't just seeing things far away, it's literally observing the past preserved in light that has travelled for billions of years to reach our instruments. The universe is expanding, which means space itself stretches as time passes, and this expansion has a measurable effect on the light travelling through it. When a galaxy emits light, that light consists of photons with specific wavelengths determined by the elements in the galaxy's stars and gas, and as those photons journey across expanding space, their wavelengths get stretched proportionally to how much the universe has expanded since the light began its journey. The physics underlying this measurement technique connects directly to Einstein's general relativity, which describes space and time as a unified fabric that can bend, stretch, and curve in response to mass and energy. Cosmic expansion means every point in space is moving away from every other point, not because galaxies are flying through space like projectiles, but because space itself is growing, carrying galaxies along with it. The analogy often used involves dots on a balloon's surface, where inflating the balloon makes all dots move apart from each other, not because the dots themselves are moving across the rubber, but because the rubber surface between them is expanding. This expansion affects light waves travelling through space by stretching their wavelengths in direct proportion to how much space has expanded during the light's journey, and astronomers can measure this stretching by comparing the wavelengths of spectral lines in distant galaxy light to the known wavelengths those same lines have in laboratory conditions. Every element produces characteristic patterns of spectral lines when its electrons jump between energy levels, creating a unique fingerprint that identifies the element and provides a reference for measuring redshift. Hydrogen, the most abundant element in the universe, produces a series of lines in the ultraviolet part of the spectrum called the Lyman series, with the strongest line at a wavelength of 121.6 nanometers called Lyman alpha. When astronomers observe a galaxy at high redshift, that Lyman alpha line no longer appears at 121.6 nanometers, but instead shows up at much longer wavelengths in the infrared part of the spectrum. And by measuring exactly where the line appears, they can calculate how much the wavelength has been stretched and therefore how much the universe has expanded since the light was emitted. A galaxy at redshift 10 has its Lyman alpha line stretched to about 1338 nanometers, meaning the wavelength has increased by a factor of 11 because redshift z equals 10 means the universe was 11 times smaller when the light began its journey. This mathematical relationship between redshift and cosmic expansion allows astronomers to convert redshift measurements into look-back times and distances using models of how the universe's expansion rate has changed over cosmic history. This stretching shifts light toward the red end of the electromagnetic spectrum, a phenomenon called redshift, and astronomers quantify this shift using a value called z that directly relates to how much the universe has grown since the light was emitted. A galaxy at redshift z equals 1 means we're seeing it when the universe was half its current size, while z equals 10 represents a time when the universe was roughly 11 times smaller than today, and the higher the redshift value, the farther back in time and space we're looking. JD's GS Z-14-0, the record-breaking galaxy discovered in 2024, has a redshift of z equals 14.32, meaning its light has been travelling toward us since the universe was just 290 million years old, while MOM Z14 pushes even further back with z equals 14.44, placing it at 280 million years after the Big Bang. The James Webb Space Telescope's ability to detect these incredibly distant objects stems from its design as an infrared observatory optimized specifically for observing the redshifted light from early galaxies. The telescope's primary mirror measures 6.5 meters across, composed of 18 hexagonal segments coated with gold to enhance infrared reflectivity, and this large collecting area allows JWST to gather enough photons from faint distant sources to produce usable spectra. The mirror's segmented design was necessary because a single 6.5-meter mirror would have been too large to fit inside any existing rocket, so engineers developed a folding configuration where the mirror launched in sections and unfolded after reaching space. A complex deployment sequence that had to work perfectly on the first try since JWST orbits too far from Earth for astronaut servicing missions. Positioned at the second Lagrange point about 1.5 million kilometers from Earth, JWST maintains a stable orbit where Earth's gravity and the Sun's gravity balance, allowing the telescope to stay in roughly the same orientation relative to Earth and Sun while requiring minimal fuel to maintain its position. This location places the telescope far beyond Earth's orbit, where it can observe without interference from our planet's infrared glow. And a massive sunshield the size of a tennis court keeps the telescope's instruments cold by blocking heat and light from the Sun, Earth, and Moon. The sunshield consists of 5 layers of material thinner than a human hair, separated by gaps that create insulating vacuum spaces, and it maintains a temperature difference of more than 300 degrees Celsius between the hot sun-facing side reaching about 85 degrees Celsius and the cold telescope side dropping below negative 233 degrees Celsius. This extreme cooling is essential because infrared detectors must operate at temperatures close to absolute zero to avoid being blinded by their own thermal radiation. And JWST's instruments cool to operating temperatures around 40 Kelvin or about negative 233 degrees Celsius through passive cooling from the sunshield plus active cooling systems for the mid-infrared instrument that needs even lower temperatures. The near-infrared camera, NIRCam, serves as the telescope's primary imager and can detect light from 0.6 to 5 microns in wavelength, covering the range where light from galaxies at redshift 10 to 20 appears after being stretched from its original ultraviolet and visible wavelengths. The near-infrared spectrograph, NIRSpec, can simultaneously obtain spectra of up to 100 objects using a microshutter array with thousands of tiny controllable shutters that open to let light through from selected targets while blocking light from surrounding sources. This multiplexing capability revolutionizes spectroscopy of distant galaxies because earlier spectrographs could observe only one object at a time, making surveys of dozens or hundreds of high redshift galaxies prohibitively time-consuming. But NIRSpec allows astronomers to confirm the distances of many galaxy candidates in a single observation. The instrument achieves spectral resolutions ranging from about 100 for low-resolution surveys to about 2,700 for detailed studies of individual spectral lines, and this resolving power lets researchers measure not just redshifts, but also chemical abundances, stellar ages, gas temperatures, and black hole masses through analysis of line widths and strengths. These measurements aren't simple estimations. They require sophisticated spectroscopy, where astronomers break down the light from a distant galaxy into its component wavelengths and identify specific spectral lines produced by known chemical elements. Hydrogen, for instance, produces a characteristic pattern of lines in the ultraviolet part of the spectrum. But when that hydrogen is in a galaxy at redshift 14, those ultraviolet lines get shifted all the way into the infrared, which is why JWST's infrared capabilities are so crucial for this work. The Hubble Space Telescope, which sees primarily invisible light, was effectively blind to these extremely distant objects because their light had been shifted entirely out of Hubble's detection range. Measuring redshifts spectroscopically provides the most reliable distance estimates because it doesn't depend on assumptions about what the galaxy looks like or how bright it should be. It simply measures the objective fact of how much the light has been stretched. Earlier JWST discoveries relied partly on photometric redshifts, which estimate distance by comparing a galaxy's brightness at different wavelengths, and while this technique can be accurate, it's also more prone to errors and can occasionally misidentify closer galaxies as more distant ones. The JD's team spent 75 hours conducting spectroscopy on faint early galaxies to confirm their distances definitively, and when the data came back showing JD's JWST C14-0 at redshift 1432, they knew they had pushed the observational boundary of cosmic time back to an unprecedented era. The confirmation process involved not just measuring the redshift, but also analysing the galaxy's properties to ensure it wasn't some closer foreground object masquerading as an ancient system. JD's JWST 14-0 measures over 1,600 light-years in diameter and shines with a luminosity that can only be explained by young stars rather than emission from an accreting black hole. which makes its existence at such an early time all the more puzzling because forming that many stars that quickly shouldn't have been possible. Brant Robertson noted that they could have detected this galaxy even if it were 10 times fainter, which means there could be other examples yet earlier in the universe, probably into the first 200 million years after the Big Bang. Understanding what 280 to 300 million years after the Big Bang actually means requires some perspective on cosmic history, because while that sounds like an enormous span of time, it's remarkably brief in the context of the universe's 13.8 billion year existence. To put it in context, as one researcher noted, sharks have been around on Earth for a longer time span than these galaxies had existed when they formed, which illustrates just how close to the beginning of everything these observations are reaching. The Big Bang occurred 13.8 billion years ago. The cosmic microwave background radiation that fills the sky today was released when the universe was 380,000 years old, and the first stars are thought to have ignited somewhere around 100 to 200 million years after the Big Bang, which means these galaxies appeared during or immediately after the epoch when the universe was just learning to make stars at all. The period from about 100 million to 1 billion years after the Big Bang is known as cosmic dawn, or the epoch of Reionization, representing a transformational phase when the first luminous objects ended the cosmic dark ages and filled the universe with light. Before this epoch, the cosmos was filled with neutral hydrogen gas that made it opaque to high-energy radiation, creating what scientists call the Dark Ages because no discrete sources of light existed yet. When the first massive stars formed, their intense ultraviolet radiation began ionizing that neutral hydrogen, separating electrons from protons and making the universe transparent. And this reionization process is thought to have unfolded over several 100 million years as more and more stars and galaxies contributed their radiation to the growing ionized bubbles that eventually merged to fill all of space. The physics of reionization involves understanding how ultraviolet photons with energies above 13.6 electron volts can split neutral hydrogen atoms into their constituent protons and electrons, and calculating how many such photons are needed to ionize all the hydrogen in the universe requires accounting for both the initial ionization and the subsequent recombination, where ionized protons and electrons occasionally come back together to form neutral atoms again. Each cubic meter of space at the relevant densities and temperatures contains billions of hydrogen atoms that must be ionized, and once ionized, a certain fraction will recombine on timescales of thousands to millions of years, depending on local conditions, meaning the universe needs a continuous supply of ionizing photons to maintain ionization against ongoing recombination. Astronomers talk about a photon budget that quantifies how many ionizing photons stars and other sources must produce to complete reionization within the observed time frame, and this budget depends on the efficiency with which stars produce ionizing photons, how many of those photons escape from their host galaxies rather than being absorbed by local gas and dust, and how long reionization takes because longer timescales allow more recombination requiring more total photons. Observations of distant quasars that probe the state of intergalactic gas through absorption, features in their spectra, indicated that reionization completed around 1 billion years after the Big Bang, with some evidence suggesting it might have finished slightly earlier or later, depending on which quasar sightlines you examine and how you interpret the data. JWST observations upended this picture by revealing far more galaxies in the early universe than models predicted, and crucially, these galaxies are producing ultraviolet light at rates 4 times higher than pre-JWST estimates suggested, according to Hakima Tech's analysis of the faintest early galaxies the telescope detected. More galaxies producing more ionizing photons means the photon budget gets balanced much earlier, potentially completing reionization by 700 to 800 million years after the Big Bang rather than the billion years indicated by quasar observations. This creates what researchers call the photon budget crisis, a tension between JWST observations suggesting rapid early reionization and quasar observations indicating reionization continued until much later times. The crisis deepens when you recognize that if reionization had completed by 700 million years, all the neutral hydrogen in the universe would have been ionized by that time, yet quasar spectra at redshifts corresponding to 900 million years after the Big Bang still shows signatures of significant neutral hydrogen remaining in intergalactic space. These signatures take the form of absorption troughs, where neutral hydrogen along the line of sight to the quasar absorbs light at specific wavelengths, creating dark gaps in the quasar's spectrum and the depth and frequency of these absorption features indicate how much neutral hydrogen exists between us and the quasar. The observation suggests substantial neutral fractions persisting well beyond when JWST data implies reionization should have finished. Julian Munoz at Harvard, who studies reionization theory, explained that reionization represents the last major change to happen in the universe, transforming everything from neutral and cold and boring to ionized and hot. And it's an accounting game where scientists know all hydrogen was neutral before reionization and ionized afterward. So the question becomes tracking how that transition occurred and what sources provided the necessary energy. The fact that JWST finds more sources producing more energy than expected should mean reionization happened faster, yet other evidence suggests it happened slower, creating a paradox that hasn't yet been resolved. Finding fully formed massive galaxies at 280 million years places them right at the dawn of cosmic dawn itself, potentially even before reionization had properly gotten underway, and this creates severe problems for models of how structure formation works. The first stars formed from primordial gas containing only hydrogen and helium left over from the Big Bang, with none of the heavier elements that would be created by subsequent stellar generations, and these population 3 stars are predicted to have been enormous, perhaps 30 to 300 times the mass of our Sun, and millions of times as bright, burning through their fuel in just a few million years before exploding as supernovae. Those explosions would have enriched the surrounding gas with the first heavy elements, allowing the next generation of stars to form with slightly different properties. And over time, this process should have built up galaxies gradually from small beginnings. The discovery of large mature galaxies at 280 to 300 million years suggests this process happened far more rapidly than theory allows, or alternatively that some entirely different mechanism accelerated structure formation in the early universe. Charlotte Mason at the Niels Bohr Institute studies galaxy formation rates across cosmic time, and noted that Hubble observations showed the rate of star formation was relatively constant as far back as about 600 million years after the Big Bang, but the JWST results imply that at earlier times the pace was much more rapid, potentially as fast as if gas clouds were collapsing and forming stars with no resistance from heat or other factors that normally slow the process down. Hakim Atek at the Institut Astrophysique de Paris found that even the faintest early galaxies JWST has spotted are producing loads of reionizing light, about 4 times as much as expected, and despite their dimness, there are enough of these galaxies to reionize the universe mostly on their own. This creates what researchers are calling a photon budget crisis, because the observations suggest more ionizing radiation should have been available earlier in cosmic history than models predict, which means reionization should have completed much faster than other evidence indicates. Sarah Bosman at the Max Planck Institute for Astronomy used observations of distant quasars to determine that reionization ended about 1.1 billion years after the Big Bang, which is 200 million years later than previously thought. Yet if JWST is revealing ultra-bright huge galaxies blazing brilliantly at 750 million years, why did the reionization process take as long as it apparently did? These contradictions point to something fundamental missing from our understanding, whether it's the physics of how gas collapses into stars, the properties of dark matter that provides the gravitational scaffolding for structure formation, or even the timeline of cosmic expansion itself. The observations aren't just slightly off from predictions, they represent discrepancies large enough that some researchers are questioning whether the entire cosmological framework needs revision, and that's a prospect that makes scientists deeply uncomfortable, because the standard model has been so successful at explaining so many other phenomena. The size and maturity of early galaxies represent only part of the puzzle, because what makes these discoveries truly baffling is how complete and well-developed these systems appear when observed at times that should show only primitive proto-galaxies. Joel Leger at Penn State captured the crisis perfectly when he stated that looking into the very early universe for the first time, they had no idea what they were going to find, and it turned out they found something so unexpected it actually creates problems for science, calling the whole picture of early galaxy formation into question. The most massive galaxies identified in JWST's deep field observations don't just exist too early, they look wrong in fundamental ways that challenge everything cosmologists thought they understood about how galaxies grow. The theoretical framework these observations violate is built on decades of research, combining observations, simulations, and physical modelling of how matter behaves under gravity in an expanding universe. Galaxy formation theory predicts that structures assemble hierarchically through a process where small dark matter halos form first from the gravitational collapse of slightly overdense regions in the early universe, and these halos then attract normal matter in the form of hydrogen and helium gas that falls into the potential wells created by dark matter's gravity. Once enough gas accumulates in a halo, it cools and condenses until reaching densities and temperatures where nuclear fusion ignites, creating the first stars, and those stars then group together into the first galaxies that merge over time to build progressively larger systems. This hierarchical assembly process operates on timescales determined by the strength of gravity and the initial density contrasts in the early universe, both of which are well constrained by observations of the cosmic microwave background and by measurements of structure in the nearby universe. Simulations that follow dark matter particles through billions of years of cosmic evolution reliably reproduce the large-scale structure we observe today, including the cosmic web of filaments and voids, the sizes and masses of galaxy clusters, and the abundance of galaxies of different masses at different cosmic epochs. These simulations predict that at 300 to 500 million years after the Big Bang, the universe should contain mostly small proto-galaxies, with stellar masses around 10 million to 100 million solar masses, perhaps with a rare handful reaching 1 billion solar masses in the most extreme overdense regions. The galaxies JWST discovered exceed these predictions by factors of 10 to 100 in some cases, with stellar masses reaching tens of billions of solar masses when standard models predict at most a few billion, and the discrepancy becomes more severe the earlier you look. At redshift 14, corresponding to 280 million years after the Big Bang, Lambda CDM simulations produce almost no galaxies massive enough to be detected by JWST, even with its unprecedented sensitivity, yet the telescope finds these systems readily in deep field images, suggesting they're not rare statistical flukes, but represent a significant population. The probability of finding even one such object in the simulated volume corresponding to JWST's survey area is vanishingly small, yet the telescope has found dozens. Part of what makes these observations so problematic is that increasing star formation efficiency, or dark matter clustering to match the observed galaxy masses, creates conflicts with other observations that constrain those same parameters, meaning you can't simply tune the models to match JWST data without breaking agreement with cosmic microwave background measurements, nearby galaxy properties, or the large-scale distribution of structure. This is the hallmark of a genuine crisis rather than a simple puzzle, because there's no obvious parameter you can adjust to fix the discrepancy without creating new problems elsewhere. In ancient galaxies that Webb was built to spot, astronomers had not expected to see old red stars that indicate stellar populations, which have already burned through much of their fuel and evolved past their youthful blue phase. Young stars burn hot and bright in blue and ultraviolet wavelengths, which is what researchers anticipated dominating the light from early galaxies. But instead, many of the objects JWST revealed appear reddish in colour, suggesting they contain significant populations of stars that have aged hundreds of millions of years. The existence of these aged stars at cosmic times when the first generation should barely have formed creates a temporal impossibility, because you can't have grandparents when parents are still children, yet that's essentially what the observations are showing. The galaxies discovered in JWST images appear only as tiny reddish dots to the powerful telescope despite their enormous intrinsic brightness, and by analysing the light emitted by these systems, astronomers established they were viewing them in the universe's infancy only 500 to 700 million years after the Big Bang. By that time, according to standard models, galaxies should have contained no more than perhaps 1 billion stars at most, with most systems being far smaller. But the reddish dots revealed in Webb's deep fields appear 50 times more massive than predictions allowed. The most massive galaxies in the sample were estimated to have stellar masses equivalent to what our Milky Way contains today, despite our galaxy having had billions more years to accumulate its stars, and finding galaxy candidates as massive as our own galaxy, when the universe was only 3% of its current age, was astounding and deeply unsettling. Ivo Labbe at Swinburne University led the team that first documented many of these impossible early giants, and he noted that researchers expected to find only very small young galaxies this early in the universe's existence. But instead they discovered what he called monsters that had somehow fast-tracked to maturity through processes nobody could explain. The standard narrative of galaxy formation holds that structures grow hierarchically through mergers, with small galaxies combining to form larger ones over time, and in dense regions galaxies collide frequently, triggering bursts of star formation and feeding central black holes. But this process requires billions of years to produce massive systems like the Milky Way. Finding that level of mass assembly complete within just a few 100 million years implies star formation must have proceeded at rates far exceeding anything observed in the nearby universe. The revelations upended what many astronomers had thought was settled science about cosmic evolution, because the standard model that describes what the universe is made of and how it has evolved since the Big Bang, known as Lambda CDM cosmology, for the roles of dark energy and cold dark matter, had been spectacularly successful at explaining observations from multiple sources. Lambda CDM accounts for the cosmic microwave background temperature fluctuations, the abundance of light elements like hydrogen and helium, the formation of galaxies, and the large-scale structure of the universe across billions of years of cosmic history, making it the consensus framework that guided research for decades. Finding massive mature galaxies where Lambda CDM predicts only small young systems should exist represents a direct challenge to that framework. Joel Lager explained that when the universe started, it was just pretty much hydrogen and helium. So the question becomes, how did we go from this hot ball of hydrogen and helium to the diversity of galaxies and objects we see today? And that transformation process, especially involving the first generation of stars, galaxies, and black holes, represents a large mystery where significant uncertainty exists. Until James Webb, scientists never had observational data from these early epochs to help understand the physics at work, which meant theories about the first billion years were essentially educated guesses based on extrapolating backward from later observations. Now that JWST keeps finding galaxies earlier and earlier in cosmic time, researchers can finally bridge the gap between the Big Bang and the remarkable set of objects visible in our night sky. But the bridge they're building doesn't match the blueprints that theory provided. One of the most striking features in the JWST observations is that the oldest galaxies found were brighter and more active than expected, with star formation rates comparable to the 1 star per year rate of the Milky Way today, but squeezed into much more compact regions about 1/1000th the size of our galaxy. As JWST peered deeper into the early universe, examining a more recent swathe of cosmic history, up to about 750 million years after the Big Bang, it found galaxies that were still quite young and strange by modern standards, but about 1/30th the size of the Milky Way, which is still much bigger than expected, and these systems exhibited star formation rates that must have been 1,000 times higher than our galaxy's current rate. Scientists gave these objects the classification ultramassive galaxies, though the term massive here is relative since even the largest were still smaller than major galaxies today. But for their epoch they represented structures that standard theory couldn't produce. The physical impossibility of forming so many stars so quickly under standard conditions has forced researchers to consider whether something about the early universe made star formation fundamentally more efficient than it is today. Charlotte Mason suggested that maybe in the early universe, galaxies were better at turning gas into stars, meaning some mechanism accelerated the collapse of gas clouds, or reduce the heating effects that normally provide pressure to resist gravitational collapse. Stars form when cold gas clouds succumb to their own gravity, and contract until the core becomes hot and dense enough to ignite nuclear fusion. But as gas contracts, it heats up, generating outward pressure that counteracts the inward gravitational pull, and this opposition is why star formation in the modern universe takes millions of years and proceeds at relatively modest rates. If conditions in the early universe somehow suppressed this heating effect or enhanced gravitational attraction, gas clouds could have collapsed much faster, forming stars in time frames 100 or even 1,000 times shorter than what's observed locally. Alternatively, perhaps the first stars were inherently different from later generations in ways that made them form more readily from primordial gas that lacked heavy elements, since metals and dust can affect how gas cools and fragments. The first stars formed from pure hydrogen and helium, which might have allowed different physics to dominate the collapse process, and some theorists speculate that population 3 stars could have been not just more massive but potentially more numerous than current models assume, providing a way to build up large stellar populations very quickly. However, explaining the observations purely through faster star formation runs into difficulties because even at maximum possible rates, there's only so much gas available and only so much time to convert it into stars before reaching the observed epochs. Mike Boylan-Colchin calculated that even if you took everything available to form stars and snapped your fingers instantaneously, you still wouldn't be able to get galaxies as massive as what JWST found at those early times, which means star formation efficiency alone can't solve the problem. This leaves researchers searching for more exotic explanations, including the possibility that some of the light attributed to stars actually comes from other sources entirely, or that the measurements of galaxy masses contain systematic errors that make the objects appear more massive than they really are. Some scientists propose that what appears to be starlight in these early galaxies might actually be emission from accreting supermassive black holes at the galaxy's centres, because black holes pulling in gas and dust can shine incredibly brightly, sometimes outshining all the stars in a galaxy combined. Catherine Chorowski and her team at the University of Texas investigated this possibility and found that black holes do account for some of the apparent mass in certain systems, with friction in fast-moving gas around black holes emitting heat and light that makes galaxies appear much brighter and bigger than they would be if the light came only from stars. Their analysis, published in 2024, showed that the standard model of cosmology likely isn't broken by these observations, since once you properly account for black hole contributions to galaxy light, the remaining stellar masses become more consistent with what Lambda CDM predicts. This resolution, while promising for preserving the standard cosmological framework, still leaves open questions because not all the apparently massive early galaxies can be explained by black hole light contamination, and even after correcting for this effect, there remain roughly twice as many massive galaxies in Webb's data of the early universe than expected. The photon budget crisis hasn't disappeared either, since the abundance of early galaxies, regardless of their individual masses, still implies more star formation and more ionizing radiation at early times than models comfortably accommodate. Scientists find themselves in a position where they've resolved one crisis only to be confronted by lingering anomalies that suggest something more subtle but still significant remains unexplained about the early universe. Perhaps nothing JWST has revealed challenges cosmological models more profoundly than the discovery of supermassive black holes that simply have no business existing when and where they've been found. For more than 2 decades, astronomers have puzzled over how gravitational behemoths weighing millions to billions of solar masses could exist less than 1 billion years after the Big Bang, because according to widely accepted models, massive black holes did not have enough time to form through the usual processes of stellar death and mergers. Recent JWST observations have not just confirmed this problem, but made it dramatically worse by finding enormous black holes at even earlier epochs than anyone thought possible, and the telescope has also revealed systems where black holes appear to dominate their host galaxies in ways that contradict our understanding of how galaxies and black holes co-evolve. Astronomers know that most major galaxies have supermassive black holes at their centres today, with the Milky Way hosting a black hole 4 million times the Sun's mass, and giant elliptical galaxies containing black holes billions of times heavier. The standard explanation for how these monsters form involves a process starting with stellar mass black holes created when massive stars die in supernova explosions, leaving behind collapsed cores that weigh perhaps 10 to 100 times the Sun's mass. These stellar remnants can then grow by accreting surrounding gas and by merging with other black holes when galaxies collide, and over billions of years this gradual accumulation can theoretically build up supermassive black holes of the sizes we observe today. The physics of black hole growth through accretion involves a delicate balance between gravity pulling matter inward and radiation pressure pushing it outward. Because as gas falls toward a black hole, it forms a swirling accretion disk where friction between neighbouring gas streams heats the material to millions of degrees, causing it to radiate intense X-rays and ultraviolet light. This radiation carries momentum that can push on surrounding gas, and when the radiation pressure equals the inward gravitational pull, you reach the Eddington limit, the maximum rate at which a black hole can accrete matter while remaining in steady state. For a black hole of a given mass, the Eddington limit sets a maximum luminosity and a corresponding maximum accretion rate, and this limit means black holes can only grow so fast regardless of how much gas surrounds them. A black hole weighing 10 solar masses accreting at the Eddington limit would take about 50 million years to reach 1,000 solar masses, and another 50 million years to reach 100,000 solar masses, with the growth rate slowing as the black hole becomes more massive, because larger black holes have higher Eddington limits, but also require more total mass to double in size. Reaching 1 billion solar masses from a 10 solar mass seed through steady Eddington limited accretion would require about 800 million years of continuous feeding. And this timeline assumes the black hole always has access to enough gas to maintain maximum accretion rates, which is unlikely in practice because gas gets depleted, blown away by winds and outflows, or heated to temperatures where it can't cool and fall onto the black hole. The problem with this light seed model, as it's called, is that it requires time, lots of time, for black holes to grow from stellar remnants to supermassive status through accretion and mergers. Even assuming black holes feed at the maximum theoretical rate and merge efficiently whenever galaxies collide, building billion solar mass black holes takes hundreds of millions to billions of years. JWST has found black holes weighing over 1 billion solar masses at redshifts around 8 to 10, meaning they existed when the universe was only 600 to 800 million years old, and in some cases the telescope has spotted what appear to be massive black holes at even earlier times, possibly even too early for the light seed process to explain them, no matter what assumptions you make about feeding rates and merger efficiency. The time constraint becomes even more severe when you account for the fact that black hole growth isn't continuous but episodic, with periods of rapid accretion alternating with quiescent phases when little gas is available, or when feedback from the black hole's radiation and winds blows surrounding gas away before it can be consumed. Studies of black hole growth in the local universe show that most supermassive black holes spend relatively small fractions of their lifetimes actively accreting at high rates, with typical duty cycles around 10%, meaning a black hole accreting for 800 million years of Eddington-limited growth would actually need 8 billion years of total time to accommodate the quiescent periods. This makes the timeline even tighter for explaining the early supermassive black holes JWST observes. The problem with this light seed model, as it's called, is that it requires time, lots of time, for black holes to grow from stellar remnants to supermassive status through accretion and mergers, even assuming black holes feed at the maximum theoretical rate, called the Eddington limit, where radiation pressure from infalling material balances gravitational attraction. A stellar mass black hole needs hundreds of millions to billions of years to reach the masses of supermassive black holes. JWST has found black holes weighing over 1 billion solar masses at redshifts around 8 to 10, meaning they existed when the universe was only 600 to 800 million years old, and in some cases the telescope has spotted what appear to be massive black holes at even earlier times, possibly even too early for the light seed process to explain them no matter what assumptions you make. Peter van Dokkum at Yale University and his collaborators discovered one of the most puzzling objects while examining JWST archive data from the Cosmos Web survey, a strange system they nicknamed the Infinity Galaxy because it displays a highly unusual shape, resembling the infinity symbol with 2 compact red nuclei each surrounded by rings of stars. The team believes this structure formed from the head-on collision of 2 disk galaxies, but what made the discovery extraordinary was the presence of a supermassive black hole, not located inside either of the 2 galactic nuclei, but positioned right between them within a vast expanse of gas. The most plausible explanation for this configuration is that the black hole formed there directly through the collapse of a gas cloud, a process known as direct collapse that creates what researchers call heavy seed black holes. Direct collapse represents an alternative pathway to supermassive black hole formation, where instead of starting with a stellar mass remnant and building upward through accretion, a massive black hole perhaps weighing up to 1 million solar masses forms immediately from collapsing gas in the early universe under special conditions. This heavy seed mechanism would immediately create a giant black hole, solving the time problem because you start with a much larger object that can reach supermassive status more quickly. However, direct collapse requires very specific conditions that are thought to be rare, including pristine gas free of metals and heavy elements that would cool the gas and allow it to fragment into stars rather than collapsing as one massive cloud into a black hole, and finding evidence for this process has been challenging until JWST began returning data. The Infinity Galaxy discovery, if confirmed as direct collapse, would hint that nature likely makes black holes this way throughout cosmic time, rather than just in the immediate aftermath of the Big Bang. Priyamvada Natarajan at Yale, who has studied black hole formation mechanisms extensively, noted that they previously reported the first evidence for direct collapse heavy seeds using combined observations from Webb and the Chandra X-ray Observatory to detect a galaxy called UHZ-1 existing when the universe was merely 470 million years old, and the infinity galaxy black hole would have formed over 5 billion years after the Big Bang, much later than UHZ-1, which suggests direct collapse might be more common than previously thought. Other JWST discoveries have revealed what researchers initially called impossible black holes that seem to be feeding at rates exceeding theoretical limits, though subsequent analysis has shown some of these extreme feeding claims were actually measurement errors caused by dust obscuring and distorting observations. One black hole, designated ELID 568, was initially reported as consuming matter 40 times faster than should be physically possible, but when astronomers revisited the data accounting for dust absorption and scattering, they found the black hole was actually feeding at a rate consistent with standard limits, demonstrating how challenging it is to interpret observations of these distant systems correctly. Still, even with measurement corrections, JWST has confirmed the existence of supermassive black holes at distances and epochs that strain explanation, including systems like QS01, a lonely black hole weighing as much as 50 million suns that appears essentially on its own, with few stars circling it at redshift around 7. Roberto Maiolino at Cambridge, who helped reveal the nature of QS01, called it completely off the scale and unlike any black hole seen before, because it represents a whole new class of enormous naked black holes that upends textbook understanding of the young universe. Normally, astronomers find supermassive black holes sitting at the centres of galaxies surrounded by billions of stars, with the black hole mass correlating with the total stellar mass of its host galaxy through a relationship that suggests galaxies and central black holes grow together. QS01 breaks that relationship by appearing to be a massive black hole with little to no surrounding galaxy, raising the question of whether it formed first before any significant star formation occurred in its vicinity, which would completely reverse the chicken or egg problem of which came first, the galaxy or its central black hole. The standard story holds that galaxies formed first, and black holes came along only after stars gravitationally collapsed into stellar mass black holes that then merged and grew, but QS01 and similar objects suggest the black hole came well before the ordinary matter in the form of gas and stars, implying some mechanism created black holes directly in the early universe without requiring stellar progenitors. Marta Volonteri, a black hole formation expert, explained that co-authors on the QS01 discovery paper suggested its origin could be a primordial black hole or possibly dark matter that collapsed because of how it interacts with itself, meaning in any case the black hole came before the stars. Primordial black holes are hypothetical objects proposed originally by Yakov Zeldovich and Igor Novikov in 1966, and further developed by Stephen Hawking in 1971, suggesting that for a brief moment after the Big Bang, some regions of the universe contained so much mass concentrated in small volumes that they imploded directly into black holes without ever forming stars. These primordial black holes could have masses ranging from tiny fractions of a gram to millions or even billions of solar masses depending on when and how they formed, and crucially they would exist essentially from the beginning of time, giving them a head start in terms of growth and positioning them dead center in galaxies that later formed around them through gravitational attraction. Researchers using high-resolution cosmological simulations have demonstrated that massive primordial black holes concede the formation of extremely overmassive, metal-poor active galactic nuclei, as observed by JWST, reproducing the extreme black hole to stellar mass ratios and low metallicity of objects like Abell 2744 QSS01 by redshift 7. The simulations show that although primordial black holes accelerate structure formation through what's called the seed effect, where the black hole's gravity attracts surrounding matter, the strong thermal feedback from the black hole's accretion delays the onset of star formation until later times, producing short bursty episodes of star formation throughout subsequent evolution. This creates exactly the kind of black hole-dominated systems with little stellar mass that JWST has discovered. The primordial black hole explanation has the advantage of not requiring fine-tuned conditions or prolonged super-Eddington growth beyond normal rates, since the black holes start out massive and simply accrete material at standard rates over the available time. However, decades of surveys searching for evidence of primordial black holes through their Hawking radiation or gravitational effects have failed to find definitive proof they exist, which means if they do comprise any significant fraction of the universe's matter, they must be rare enough to have evaded detection so far. Recent theoretical work proposes that even a small fraction of dark matter in the form of primordial black holes could grow over the course of 100 million years in the densest collections of matter, accreting enough material to reach supermassive status in the epochs where JWST has observed them. JWST has also begun detecting what might be an entirely new class of cosmic object dubbed black hole stars, where accretion onto a black hole powers what appears to be a stellar object with properties unlike any normal star. Additionally, the telescope has found evidence of supermassive black holes growing at the centres of galaxies as early as 570 million years after the Big Bang, with systems showing rapid growth far faster than expected in galaxies at such early times. Roberta Tripodi, lead author of a study on one such system called Cannock's LRDZ86, called the discovery truly remarkable because they observed a galaxy from less than 600 million years after the Big Bang that's not only hosting a supermassive black hole, but the black hole is growing rapidly, far faster than expected, which challenges understanding of black hole and galaxy formation in the early universe. The accumulating evidence from JWST points toward multiple pathways for rapid black hole growth in the early universe, possibly including primordial black holes that form directly from density fluctuations in the Big Bang, direct collapse of massive gas clouds into million solar mass seeds, and perhaps yet undiscovered mechanisms involving dark matter interactions or exotic physics in the first moments after the Big Bang. The implications extend beyond just explaining how these particular objects formed, because if black holes did precede galaxy formation and act as seeds around which galaxies assembled, that represents a complete inversion of the standard hierarchical structure formation paradigm, and would require rethinking how cosmic evolution unfolded from the Dark Ages through cosmic dawn into the universe we observe today. Beyond the sheer existence and mass of early galaxies and black holes, JWST has revealed something perhaps even more puzzling through detailed spectroscopy that breaks down galactic light into its chemical components, and what the telescope found challenges our understanding of stellar evolution and cosmic chemical enrichment. When researchers examined GS3073, a galaxy existing in the early universe, they discovered chemical abundances that act like a cosmic fingerprint, and the pattern didn't match anything ordinary stars can produce. The extreme nitrogen abundance observed matches only one kind of source known, primordial stars thousands of times more massive than our Sun, which scientists have taken to calling monster stars because of their extraordinary properties. Harley Katz from Oxford, working with the team analysing JWST data, noted that astronomers discovered an overabundance of nitrogen in early galaxies, and there's not a single theoretical model that predicted this much nitrogen this early in cosmic history. This matters because chemical abundances tell us about stellar populations and their ages, since different elements are created through different nuclear processes in stars of various masses and at different stages of their life cycles. Hydrogen and helium were produced in the Big Bang itself, while essentially all heavier elements were forged in stars through nuclear fusion, or in the explosive deaths of stars, meaning the presence of heavy elements indicates stars have lived and died to create them, and the relative amounts of different elements provide clues about what kinds of stars did the creating. Nitrogen is particularly interesting because it's produced primarily in massive stars through a process called the CNO cycle, where carbon, nitrogen and oxygen are converted back and forth during hydrogen fusion, with nitrogen building up over the star's lifetime. Normal massive stars produce some nitrogen, but the levels JWST detected in galaxies like GS3073 far exceed what standard stellar models predict, suggesting either that the early universe contained stars much more massive than modern stars, or that some other mechanism was enriching the gas with nitrogen faster than expected. The team investigating GS3073 developed models suggesting these monster stars would have been in a specific mass range, perhaps 1,000 to 10,000 times the Sun's mass, and crucially these objects would not explode as supernovae at the end of their lives but instead collapse directly into massive black holes. This direct collapse scenario provides a potential explanation for where the seeds of supermassive black holes came from, because if the first generation of stars included these monster stars that left behind black holes, weighing thousands of solar masses when they died, those remnants could grow relatively quickly to supermassive status. The The models also predict that the nitrogen signature observed wouldn't appear in stars smaller or larger than this specific mass range, providing a testable prediction for the monster star hypothesis. Francesco D'Eugenio from Cambridge, working on observations of the earliest confirmed galaxies, emphasized that these systems join a small but growing population of galaxies from the first 500 million years of cosmic history, where researchers can really probe stellar populations and the distinctive patterns of chemical elements within them. The spectroscopic capabilities of JWST allow astronomers to detect individual elements inside galaxies through their characteristic spectral lines, achieving precision that was impossible with previous instruments. The telescope's observations revealed that GS-3073 contains an actively feeding black hole at its centre, which could be the remnant of one of these monster stars, strengthening the connection between early chemical enrichment and black hole formation. Devesh Nandal, lead author on the GS-3073 study, explained that chemical abundances act like cosmic fingerprints that can distinguish between different formation scenarios, and the extreme nitrogen pattern observed is unlike anything ordinary stars can produce, pointing uniquely toward these primordial monster stars. The presence of such massive stars in the early universe would have profound implications for understanding cosmic dawn, because stars thousands of times more massive than the Sun would burn incredibly brightly, potentially contributing substantially to the Reionization of hydrogen gas filling the universe. These objects would have been short-lived, lasting perhaps only 1 million years before collapsing. But during that time they would have pumped enormous amounts of ultraviolet radiation into their surroundings, ionizing gas and enriching it with the heavy elements created through nuclear fusion in their cores. The subsequent generation of stars forming from this enriched gas would then display the elevated nitrogen abundances that JWST detected. Another chemical signature that's proving puzzling is the low overall metallicity, meaning low abundance of all heavy elements combined in some of the earliest galaxies JWST has observed, because systems existing 300 to 500 million years after the Big Bang show metal contents that seem simultaneously too low and too high to make sense. Martin López Corredera at the Instituto de Astrofísica de Canarias led research examining galaxies at redshift close to 8, which existed when the universe was only 600 million years old, and the team inferred that the mean age of stellar populations in some of these galaxies would not be compatible with the accepted age of the universe, estimating with 95% probability that these galaxies contain stellar populations with ages between 900 and 2,400 million years. This estimate creates an impossible situation, because if stars and galaxies at 600 million years after the Big Bang have ages up to 2.4 billion years, those stars would have been formed several hundred million years before the Big Bang itself, which obviously makes no sense in the standard cosmological framework. Fulvio Melia, co-author on the study, stated that the discovery of well-formed galaxies at such an early stage in the universe's history has been very disturbing for many astronomers and cosmologists because nobody has a valid explanation for how they may have been formed, and the work showing stars apparently older than the universe itself makes the situation even more disconcerting for conventional cosmology. The research team acknowledged that their conclusions result from approximations in stellar astrophysics and models of dust extinction, meaning the estimates should be treated with appropriate caution because uncertainties in how stars evolve and how dust affects observations could shift the calculated ages downward toward more reasonable values. However, even accounting for these uncertainties, the basic problem remains that some early galaxies appear too chemically evolved for their cosmic age, containing stellar populations that seem to have been burning and producing heavy elements for longer than the time that had elapsed since the Big Bang. Kit Boyette from the University of Melbourne studied another early galaxy called JWST, seen as it was 510 million years after the Big Bang, and the team discovered that much like other early galaxies observed by JWST, JWST is far more massive and mature than expected for a galaxy in the infant universe, already containing several billion stars during the ancient time period when it was observed. More surprising still, the population of old stars in G9P3 was much larger than previously suspected, meaning galaxies became chemically mature faster than anyone had anticipated. With the rapid, efficient buildup of stars and metals tied to ongoing galaxy mergers, demonstrating that massive galaxies with several billion stars existed earlier than expected. The observations indicate that early galaxies were more luminous than predicted, forming stars at breakneck speeds in massive dense star clusters, and Angela Adamo from Stockholm University explained that astronomers are building a new understanding of how early galaxies formed based on what JWST reveals. Everything about the early universe appears to have operated more vigorously and efficiently than modern conditions allow, from star formation rates to black hole growth to chemical enrichment, and this vigour has no clear explanation within standard physics. The first stars and galaxies established the overall structure and chemical composition of the universe, and if that foundational period proceeded differently than theory predicts, the implications cascade through all subsequent cosmic history. The puzzle of chemical abundances connects to the broader mystery of how population 3 stars, the hypothetical first generation of stars containing absolutely no heavy elements, influenced later generations. Population 3 stars have never been directly observed because they formed so early and were so massive that they died quickly, leaving behind only their chemical legacy and the gas from which later stars formed. The chemical fingerprints JWST detects might be providing the first compelling evidence that these monster stars existed, offering clues about their masses, lifetimes, and deaths through the patterns of elements they left behind. Patterns that don't match anything produced by stars in the modern universe, where every star contains at least traces of heavy elements from previous generations. As JWST observations accumulated through 2023 and into 2024, the astronomical community found itself grappling with a growing divide between what the telescope was revealing and what theory predicted should exist, and this tension has sparked intense debate about whether the problem lies with the measurements, the theoretical models, or fundamental aspects of cosmology itself. Some researchers argue the observations contain systematic errors that make early galaxies appear more massive or distant than they truly are, while others contend the standard cosmological framework needs revision. And still others propose that the answer lies somewhere in between, with astrophysical processes that are poorly understood but don't require abandoning established physics. The possibility that measurements are systematically wrong centers on 2 main concerns. First, that photometric redshift estimates might be placing some galaxies farther away than they actually are, and second, that the brightness of galaxies might be misattributed to starlight when it actually comes from other sources like black holes. Early JWST discoveries relied heavily on photometric techniques that estimate distance by measuring galaxy brightness at multiple wavelengths and comparing those measurements to models of how galaxy colours change with redshift. And while this method is generally reliable, it can occasionally produce errors where a closer galaxy with unusual properties gets misidentified as an extremely distant one. Photometric redshift errors typically occur when a galaxy's spectrum contains features that mimic the appearance of high redshift systems, such as strong emission lines that happen to fall at wavelengths that look like redshifted ultraviolet features, or when dust reddening makes a nearby galaxy appear similar in colour to a distant one. The technique works by fitting galaxy spectral energy distributions, the brightness measured at different wavelengths, to templates derived from known galaxy types, and finding the redshift that produces the best match between observations and templates. This fitting process is robust when galaxies have normal properties, and when observations span a wide range of wavelengths, providing multiple constraints, but it becomes uncertain when dealing with unusual objects, or limited wavelength coverage. Some early JWST discoveries were based on photometry alone, with spectacular claims of galaxies at redshifts 16 to 20 that would place them just 100 to 200 million years after the Big Bang, and these extreme candidates generated headlines suggesting they might break cosmology. Subsequent spectroscopic follow-up of the most accessible candidates revealed that many were indeed at high redshifts, confirming photometric estimates were approximately correct, but some fraction turned out to be closer interlopers, including dusty starbursting galaxies at redshifts around 4 to 6, whose red colours mimicked the appearance of much more distant systems. The fraction of misidentifications appears to be perhaps 20 to 30% for the most extreme candidates, meaning most photometric detections are genuine, but a significant minority are errors. This realization led to more cautious interpretation of photometric candidates and greater emphasis on obtaining spectroscopic confirmation before making definitive claims about record-breaking discoveries, and the JD's team's approach of investing 75 hours in deep spectroscopy exemplifies this caution by ensuring distance measurements rest on solid spectroscopic foundations rather than photometric estimates alone. The spectroscopic confirmation of galaxies at redshifts 13 to 14 with well-measured spectra, showing multiple emission and absorption lines, eliminates distance uncertainty for these systems, establishing beyond doubt that genuinely massive galaxies exist at 280 to 330 million years after the Big Bang, even if some more extreme photometric candidates at redshift 16 to 20 prove to be erroneous. The possibility that measurements are systematically wrong centres on two main concerns. First, that photometric redshift estimates might be placing some galaxies farther away than they actually are. And second, that the brightness of galaxies might be misattributed to starlight when it actually comes from other sources like black holes. Early JWST discoveries relied heavily on photometric techniques that estimate distance by measuring galaxy brightness at multiple wavelengths and comparing those measurements to models of how galaxy colours change with redshift. And while this method is generally reliable, it can occasionally produce errors where a closer galaxy with unusual properties gets misidentified as an extremely distant one. Spectroscopic follow-up observations have confirmed that many of the most extreme early galaxy candidates are genuinely at the high redshifts initially estimated, ruling out photometric errors as a complete explanation for the discoveries, though some fraction of candidates has proven to be closer foreground objects upon detailed examination. The more significant measurement concern involves distinguishing between light from stars and light from accreting black holes, because both can make a galaxy appear bright, but for very different reasons with very different implications for mass estimates. Katherine Chwarowski's team at the University of Texas found that black holes in some early galaxies make them appear much brighter and bigger than they really are, because friction in the fast-moving gas around a black hole emits heat and light that can outshine all the stars in a galaxy combined. When astronomers observe a very bright galaxy and estimate its stellar mass based on the assumption that stars produce all the light, they overestimate the true stellar mass if a significant fraction of the light actually comes from black hole accretion. By carefully modelling the contribution of black hole emission to galaxy brightness, the researchers showed that many apparently overmassive galaxies become consistent with standard models once this effect is accounted for, and they concluded that there is no crisis in terms of the standard model of cosmology. Stephen Finkelstein at Texas, who worked on this analysis, noted that any time you have a theory that stood the test of time for so long, you need overwhelming evidence to throw it out, and the evidence for abandoning Lambda CDM simply isn't there once you properly interpret the observations. However, even after correcting for black hole contributions, roughly twice as many massive galaxies appear in Webb's data of the early universe than expected, suggesting the resolution is incomplete and some genuine tension with predictions remains. The photon budget crisis hasn't disappeared either, because the sheer number of early galaxies regardless of their individual masses still implies more star formation and ionizing radiation at early times than models comfortably predict. Mike Boylan-Colchin, who has studied the early galaxy problem extensively, stated that most people would put their money on an astrophysical explanation right now rather than a fundamental breakdown in cosmology, and he counts himself in that category because the data doesn't yet constitute overwhelming evidence that Lambda CDM is wrong. Astrophysical explanations focus on processes like star formation efficiency, dust properties, and the interplay between stars and black holes that might work differently in the early universe compared to local conditions, allowing galaxies to build up mass and brightness faster than standard assumptions predict without requiring new physics or a different cosmological model. One promising astrophysical explanation involves recognizing that JWST is only seeing young hot bright stars in the newfound early galaxies, and follow-up observations at longer wavelengths could reveal whether these systems are truly as massive as they appear, or whether most of their light comes from a relatively small population of very luminous stars that make the galaxies seem more massive than they actually are. Nashwan Sabti at Johns Hopkins University and colleagues analysed this question by combining JWST infrared observations with Hubble Space Telescope ultraviolet data that traces the brightest young stars, and they found that the star formation rates derived from UV light don't leave much wiggle room to play around with cosmology, meaning the source of ultramassive galaxies is very likely astrophysics rather than a cosmological breakdown. The analysis showed that the oldest galaxies JWST found were brighter and more active than expected, with star formation rates comparable to the Milky Way's current rate, but squeezed into regions 1/1000th the size of our galaxy, creating incredibly dense starburst environments. By comparing star formation rates to stellar masses, The researchers determined the galaxies could be explained within the confines of the cosmological model of the universe, though they do require surprisingly efficient star formation that remains to be fully understood. Alison Kirkpatrick at Kansas, who specializes in galaxy evolution, noted that Webb is finding too many too massive galaxies too early in the universe, which is surprising but not yet inexplicable. Still, the accumulation of anomalies starts to weigh against the idea that everything can be explained by astrophysics alone, because each individual discrepancy might have an astrophysical solution, but the combination of massive galaxies, enormous black holes, high chemical abundances and more galaxies overall than predicted starts to suggest something more systematic could be wrong. Some researchers point to the fact that JWST was not expected to find any galaxies as early as it has, at least not at this stage of the mission with relatively shallow observations. Yet it's found not just one or two, but dozens of extremely distant systems, and if the telescope continues finding galaxies pushing back toward 200 million years after the Big Bang or earlier, the case for new physics becomes stronger. Another concern involves the properties of galaxies at intermediate redshifts that should represent a more established era of galaxy formation, but still show puzzling characteristics, including so-called sleeping beauty galaxies that appear dormant and not forming stars despite existing at cosmic times when star formation should be vigorous. Additionally, JWST has discovered more than 300 mysterious little red dots, compact objects whose nature remains debated, with some researchers arguing they're obscured black holes, while others suggest they might be unusually dense galaxies, or even new types of objects not predicted by any model. The spirited debate over little red dots illustrates how challenging it is to interpret JWST observations correctly, because these objects display some classic features of glowing black holes but not others, and estimates of their masses have been somewhat indirect until detailed spectroscopic analysis became available. Very rarely do astronomers find things they can't explain, as one researcher noted, and the field has become obsessed with trying to understand what these enigmatic objects represent, and whether they're connected to the broader questions about early galaxy and black hole formation. Observations published in 2024 and 2025 have begun resolving some of these mysteries, with spectroscopy confirming that many little red dots do contain actively accreting supermassive black holes, though the question of why they're so compact and numerous remains open. The resolution of individual mysteries doesn't necessarily resolve the overall tension, however, because each solution seems to raise new questions about why the early universe operated the way it apparently did, and whether the processes driving galaxy evolution in cosmic dawn were truly just more vigorous versions of modern phenomena or something fundamentally different that our theories haven't captured. Lambda CDM cosmology, named for its key components of dark energy represented by lambda and cold dark matter abbreviated CDM, has been the dominant framework for understanding cosmic evolution since the 1990s, when observations of distant supernovae first revealed that the universe's expansion is accelerating. The model successfully explains the cosmic microwave background radiation's temperature fluctuations, the large-scale distribution of galaxies across billions of light-years, the abundances of light elements created in the first few minutes after the Big Bang, and the overall expansion history of the universe, making it spectacularly successful across multiple independent lines of evidence. Finding observations that challenge Lambda CDM is therefore a big deal, because it means either the observations are wrong, the model needs modification, or our understanding of physics on cosmic scales requires revision. The core of Lambda CDM rests on general relativity describing how gravity works, combined with specific assumptions about the universe's content, including about 68% dark energy that drives accelerated expansion, roughly 27% dark matter that provides gravitational scaffolding for structure formation, and about 5% normal matter that makes up everything we can see, including stars, gas, and dust. The model assumes the universe is roughly homogeneous and isotropic on large scales, meaning it looks statistically the same in all directions and at all locations when averaged over sufficiently large volumes, and this cosmological principle simplifies the mathematics enormously by allowing scientists to model the entire universe using relatively straightforward equations. The model's successes are numerous and compelling, starting with its explanation of the cosmic microwave background, which appears as nearly uniform radiation at a temperature of 2.7 Kelvin filling all of space, with tiny fluctuations of about 1 part in 100,000 that encode information about the universe's composition and geometry when the radiation was released 380,000 years after the Big Bang. Lambda CDM predicts the exact pattern of these fluctuations based on known physics of how sound waves propagated through the hot plasma of the early universe, and measurements from satellites match these predictions with stunning precision, determining cosmological parameters like the universe's age, the Hubble constant, and the densities of different components to accuracies of a few percent or better. The model also explains the abundance of light elements produced in the first few minutes after the Big Bang through nuclear reactions that fused protons and neutrons into deuterium, helium, and trace amounts of lithium, and the predicted abundances of these elements depend sensitively on the density of normal matter and the expansion rate during those early moments. Observations of primordial gas clouds that haven't been enriched by stellar nucleosynthesis show deuterium and helium abundances matching Lambda CDM predictions, providing independent confirmation that the model correctly describes conditions in the first few minutes of cosmic history. The large-scale distribution of galaxies traced by surveys like the Sloan Digital Sky Survey reveals a cosmic web structure with filaments, walls, and voids that simulations based on Lambda CDM reproduce in remarkable detail, matching not just the overall pattern but also statistical properties like the distribution of galaxy cluster masses and the correlation functions describing how galaxies cluster together. These successes across different epochs and different types of observations make Lambda CDM robust and resistant to abandonment based on any single problematic observation, because the model has passed so many independent tests that finding one area of disagreement doesn't necessarily invalidate the entire framework. However, JWST observations challenge Lambda CDM in ways that are difficult to dismiss as simple anomalies or measurement errors, because the problems appear systematically across multiple aspects of early galaxy formation rather than being isolated to one particular property or one particular galaxy. The core of Lambda CDM rests on general relativity describing how gravity works, combined with specific assumptions about the universe's content, including about 68% dark energy that drives accelerated expansion, roughly 27% dark matter that provides gravitational scaffolding for structure formation, and about 5% normal matter that makes up everything we can see, including stars, gas, and dust. The model assumes the universe is roughly homogeneous and isotropic on large scales, meaning it looks statistically the same in all directions and at all locations when averaged over sufficiently large volumes. And this cosmological principle simplifies the mathematics enormously by allowing scientists to model the entire universe using relatively straightforward equations. Structure formation in Lambda CDM proceeds through gravitational amplification of tiny density fluctuations created during cosmic inflation in the first fraction of a second after the Big Bang, with slightly denser regions pulling in more matter over time and collapsing to form the first stars and galaxies while underdense regions became voids. The process is hierarchical, with small structures forming first and merging over time to build progressively larger galaxies and galaxy clusters, and simulations based on this framework reproduce the large-scale cosmic web of filaments and clusters observed in galaxy surveys. The model predicts star formation rates should increase gradually over the first billion years as more and more gas collapses into galaxies, reaching a peak around 2 to 3 billion years after the Big Bang before declining as available gas gets exhausted. JWST observations challenge several aspects of this picture, most directly the timeline and efficiency of structure formation, because finding massive galaxies and supermassive black holes at 300 million years implies structures assembled faster than Lambda CDM comfortably allows. The model can accommodate some early massive objects through rare statistical fluctuations, where particularly dense regions happen to form, but the abundance of such systems discovered by JWST strains probability, with some estimates suggesting objects like the KBC void or certain early galaxies represent 10 sigma deviations from predicted distributions, meaning you'd expect to find them only once in trillions of universe-sized volumes. If JWST keeps finding structures that are too large too early too often, the case for modifying the model strengthens, and several proposals have been advanced for how Lambda CDM might need to change. One possibility is that the initial density fluctuations from cosmic inflation were not as smooth as standard inflationary models predict, with more power on large scales that would allow bigger structures to form earlier. Another option involves changing assumptions about dark matter, perhaps by adding interactions between dark matter particles that go beyond pure gravity, allowing dark matter to clump more efficiently and accelerate structure formation. A particularly intriguing proposal involves ultra-self-interacting dark matter, where a small fraction of dark matter particles, less than 10% of the total, exhibit strong self-interactions that cause them to scatter off one another, much more effectively than standard dark matter does through gravity alone. Grant Roberts, a doctoral student at UC Santa Cruz working on this idea, explained that dark matter self-interaction is necessary because the particles need a way to scatter that's stronger than gravitational interactions, and this scattering causes dark matter to bunch up in the very inner central regions of galactic halos, allowing them to collapse into supermassive black hole seeds. Simulations using this model successfully reproduce the observed quasars' parameters, including their masses and ages, even under different assumptions about how the self-interaction strength depends on velocity. The ultra-self-interacting dark matter hypothesis makes testable predictions, particularly suggesting the existence of intermediate mass black holes in dwarf galaxies, and if observations confirm this prediction, it would provide support for the model beyond just explaining early supermassive black holes. Other modified dark matter proposals include warm dark matter that moves faster than standard cold dark matter, potentially affecting small-scale structure formation, or fuzzy dark matter composed of ultralight particles that behave more like waves than particles on small scales, altering how dark matter halos form and evolve. An entirely different approach questions whether general relativity accurately describes gravity on cosmological scales, because while Einstein's theory has passed every test in the solar system, and with binary pulsars, it's never been directly tested at distances of millions or billions of light-years where dark matter and dark energy effects dominate. Modified gravity theories propose that gravity works differently on large scales than general relativity predicts, either becoming stronger at large distances or depending on the environment in ways that could accelerate structure formation without requiring as much dark matter. Modified Newtonian dynamics, proposed by Mordechai-Milgrom in 1983, suggests gravity becomes stronger than Newton's laws predict when accelerations are extremely small, as they are on galaxy scales. And while MON struggles to explain many cosmological observations, it does predict more vigorous structure formation that could help account for large early structures. Some researchers argue that the simplest explanation for JWST's findings is that the universe is simply older than the standard 13 to 8 billion year estimate, giving more time for structures to form and evolve to the states observed. Rajendra Gupta at the University of Ottawa has proposed a hybrid model combining elements of the standard Big Bang expansion with tired light theories where photons lose energy as they travel cosmic distances, and he claims this model doubles the universe's age to around 27 billion years, while still fitting observations of supernovae redshifts and the cosmic microwave background that caused tired light to be rejected decades ago when proposed in isolation. Gupta's model stretches galaxy formation time 10 to 20-fold over the standard model, giving enough time for well-evolved galaxies to form at the redshifts where JWST finds them. And he points out that the new model incorporates evolving coupling constants, proposed by physicist Paul Dirac in 1937, where fundamental physical constants might change slowly over cosmic time. The tired light component explains why high redshift galaxy sizes fit JWST observations admirably well, since in tired light models the universe doesn't expand as rapidly as in standard cosmology, meaning objects at a given redshift are actually closer and therefore appear larger than they would in the standard model. Critics note that tired light models historically failed to explain several key observations, including the time dilation of supernova-like curves and the uniformity of the cosmic microwave background. And while Gupta claims his hybrid model addresses these issues, the proposal hasn't gained widespread acceptance because it requires accepting a framework that departs significantly from well-tested physics. The allure of an older universe is strong, however, because it elegantly solves multiple problems simultaneously by simply giving more time for everything to happen. And if future observations continue piling up evidence for structures that are too evolved too early, the case for revisiting fundamental assumptions about cosmic expansion and the age of the universe will grow stronger. Another speculative possibility is that the universe might be fundamentally inhomogeneous on scales we previously thought were homogeneous, meaning large-scale structure is more extreme than Lambda CDM predicts, with bigger voids and denser filaments, creating a more dramatic cosmic web. This would affect observations by creating local variations in expansion rates and structure density that could masquerade as either overly mature structures in some regions or as systematic biases in our measurements if we happen to be located in an unusual region. Lior Shamir at the Carla Ice College of Engineering found evidence that galaxies observed by JWST show a preferred rotation direction, rather than the 50-50 split expected in a truly random universe, with about 2/3 rotating clockwise and 1/3 counterclockwise, and he suggested this might indicate the universe was born rotating, potentially as the interior of a black hole in a larger parent universe. This black hole cosmology, or Schwarzschild cosmology, proposes our observable universe might itself be inside a black hole, which would naturally produce rotation and could affect how structure forms, though the idea remains highly speculative and faces numerous challenges in explaining detailed observations. The mere fact that such ideas are being seriously discussed by researchers indicates how profound the challenge posed by JWST observations has become, because under normal circumstances scientists don't propose that we're living inside a black hole, or that the universe is twice as old as thought, unless the evidence forces consideration of dramatic alternatives to established theory. Perhaps no question strikes more directly at the heart of cosmology than asking how old the universe actually is, because this single number encapsulates everything about cosmic expansion history, the formation timeline for all structures, and the fundamental properties of space, matter, and energy. The current standard value of 13.8 billion years comes from detailed analysis of the cosmic microwave background radiation measured by satellites including the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft. And these measurements are incredibly precise with uncertainties of only about 20 million years. The age estimate depends on knowing the universe's expansion rate today, called the Hubble constant, and on understanding how that expansion rate has changed over time due to the competing influences of matter's gravity slowing expansion and dark energy's repulsive effect accelerating it. The cosmic microwave background age determination works by measuring the angular scale of acoustic oscillations imprinted in the radiation's temperature pattern, oscillations that represent sound waves frozen into the structure of the universe when atoms first formed, and these oscillations have a characteristic scale determined by the distance sound could travel in the 380,000 years between the Big Bang and recombination. By measuring how large these oscillations appear on the sky, and combining that with knowledge of how far away the cosmic microwave background surface is, cosmologists can determine the geometry and expansion history of the universe, which directly gives its age. The method is robust because it depends on well-understood physics of atomic interactions, sound wave propagation, and gravitational dynamics, all tested extensively in laboratory and observational contexts. Independent age measurements come from several sources that constrain how old the universe can be, starting with radioactive dating of the oldest objects we can observe. Certain heavy elements like uranium-238 and thorium-232 decay at precisely known rates with half-lives of 4.5 billion years and 14 billion years respectively. And by measuring the abundances of these elements and their decay products in ancient stars, astronomers can determine when the elements were created. The oldest stars show uranium to thorium ratios indicating the elements formed about 13 to 14 billion years ago, consistent with the cosmic microwave background age, and providing independent confirmation from completely different physics. White dwarf stars offer another age constraint through their cooling rates, because white dwarfs are stellar remnants that no longer generate energy through fusion, but simply radiate away their stored thermal energy, cooling gradually over billions of years until they become dark cinders. The coolest white dwarfs in our galaxy have surface temperatures around 3000 Kelvin, indicating they've been cooling for approximately 12 to 13 billion years, setting a lower limit on the age of the Milky Way and therefore the universe. This measurement doesn't depend on cosmological models or expansion rates, but simply on understanding how hot objects cool, governed by thermodynamics and the physics of dense matter, and the ages derived match the cosmic microwave background determination within uncertainties. JWST observations threaten this carefully constructed age estimate in two ways. First, by finding structures that appear too evolved for the available time if the universe is only 13.8 billion years old, and second, by potentially indicating the local expansion rate is higher than the cosmic microwave background-derived value, which would make the universe younger rather than older and create conflicts with stellar age measurements. The tension comes into sharp focus when examining the oldest stars in our galaxy, which exist in globular clusters in the galactic halo, and appear to be about 12.5 to 13 billion years old, based on stellar evolution models that predict how stars of different masses burn through their fuel and evolve through various stages. These stellar age measurements are robust and consistent across many clusters using different techniques, with the Gaia space mission providing precise distances through parallax that removed one major source of uncertainty in age calculations. Finding stars that are 13 billion years old fits comfortably within a universe that's 13.8 billion years old, allowing 800 million years between the Big Bang and the formation of the first stars in our galaxy. But if the universe is significantly younger, or if the oldest stars are significantly older than current estimates, the timeline doesn't work. Martin Lopez Correduera's analysis suggesting some JWST observed galaxies contain stellar populations with ages between 900 and 2400 million years, when observed at 600 million years after the Big Bang would require those stars to have formed before the Big Bang, which is obviously impossible. Correduera acknowledges the results depend on approximations in stellar astrophysics and models of dust extinction that could shift the calculated ages, but he and co-author Fulvio Melia suggest considering alternative cosmological models like the RH=CT model proposed by Melia, which assumes an expanding universe with a beginning similar to the standard model, but expanding at a constant rate without the acceleration attributed to dark energy. In this model, the age of the universe corresponding to galaxies observed at redshift 8 would be 1.5 billion years, instead of 600 million years in the standard model, solving the age problem by providing more time for stars to form and evolve before being observed. Constant expansion cosmologies eliminate dark energy and modify the relationship between redshift and cosmic time, making the universe appear older at any given redshift compared to accelerating expansion models. And if observations continue suggesting stellar populations are older than standard models allow, pressure will grow to seriously consider whether cosmic expansion has been constant rather than accelerating. However, constant expansion models face severe challenges in explaining other observations, including supernova data that originally revealed acceleration and the specific pattern of temperature fluctuations in the cosmic microwave background that are best fit by models including dark energy. The possibility that the universe is roughly twice as old as currently thought, around 26 to 28 billion years instead of 13.8 billion years, would revolutionize our understanding by allowing ample time for all the structures JWST observes to form through standard processes without requiring dramatically enhanced efficiency or exotic physics. An older universe would mean galaxies at redshift 14 didn't form at 300 million years, but rather at perhaps 2 to 3 billion years after the Big Bang, providing 10 times more time for stars to form, black holes to grow, and chemical enrichment to occur. The challenge is reconciling this older age with observations that appear to constrain the age quite precisely, including not just the cosmic microwave background, but also the abundances of radioactive elements like uranium and thorium that decay at known rates and provide independent age estimates. Rajendra Gupta's hybrid model attempts to thread this needle by combining tired light effects that alter the redshift distance relationship with evolving physical constants that change how matter and radiation evolve over time, and while his model doubles the age, it does so in a way that he claims remains consistent with multiple observational constraints. Critics remain skeptical because the model introduces several new parameters that must be carefully tuned to match observations, and Occam's razor suggests preferring the simpler standard model unless the evidence overwhelmingly demands the more complex alternative. The evidence from JWST is certainly surprising and challenging, but whether it rises to the level of overwhelming remains a matter of debate. One way to potentially resolve the age controversy is through more detailed observations of stellar populations in early galaxies, because if JWST can obtain deep spectroscopy of enough early galaxies to reliably measure ages for their stars, researchers can test whether the apparent age problem is real or an artifact of measurement uncertainties and modelling assumptions. Initial spectroscopic observations suggest some early galaxies do contain surprisingly old stellar populations based on their chemical compositions and the colours of their light, but more data is needed to establish statistical significance and rule out alternative explanations like dust reddening that could mimic the effects of stellar aging. Another critical test involves pushing observations to even earlier epochs beyond redshift 15 toward the first 200 million years after the Big Bang, because if galaxies continue appearing well-formed and massive all the way back to that era, the case for dramatically revising our timeline becomes compelling. Conversely, if there's a boundary somewhere around redshift 15 to 20 beyond which galaxies become noticeably smaller and less mature, that would indicate structure formation did eventually run out of time at sufficiently early epochs, supporting the idea that what JWST observes at redshift 10 to 14 represents unusual but not impossible fluctuations, rather than evidence of a systematically wrong age for the universe. The implications of JWST's discoveries extend far beyond just revising estimates for when galaxies formed or how massive black holes grew, because if the observations force changes to fundamental cosmology, those changes ripple through every aspect of our understanding about where we came from and where we're going. Dark matter, which makes up about 85% of all matter in the universe, provides the gravitational scaffolding that allows normal matter to collapse into stars and galaxies, and Lambda CDM assumes dark matter is cold, meaning its particles move slowly enough that they clump efficiently on all scales from dwarf galaxies to superclusters. If structure formation proceeded more rapidly than cold dark matter allows, either because of enhanced dark matter interactions or because of modifications to gravity itself, the nature of dark matter might be different than we've assumed. The properties of dark matter remain one of physics' greatest unsolved mysteries despite decades of theoretical and experimental work, because while we can measure dark matter's gravitational effects through galaxy rotation curves, gravitational lensing, and large-scale structure, we have no direct detection of dark matter particles and no confirmed identification of what those particles are. The leading candidate is weakly interacting massive particles, or WIMPs, which would be heavy elementary particles produced in the early universe that interact only through gravity and possibly the weak nuclear force, making them extremely difficult to detect, despite experimental efforts involving sensitive detectors deep underground, shielded from cosmic rays and other backgrounds. Self-interacting dark matter models where particles scatter off each other beyond pure gravitational interactions have been proposed to explain various puzzles in small-scale structure, including why dwarf galaxy centers appear less dense than pure cold dark matter predicts, because collisions between dark matter particles would transfer momentum and energy, heating the centers of dark matter halos and making them less concentrated. JWST's findings add another potential motivation for considering such models, since they can accelerate black hole formation in the early universe through the mechanism Grant Roberts and colleagues described, where self-interactions cause dark matter to bunch up in galactic centers, allowing collapse into massive black hole seeds. If future observations confirm predictions of these models, including the presence of intermediate mass black holes in dwarf galaxies, it would suggest dark matter is more complex than the simplest cold dark matter scenario, and might involve new particle physics beyond the standard model. Alternative dark matter candidates include axions, which are ultralight particles predicted by some extensions of particle physics that solve problems with the strong nuclear force, and these particles would behave more like waves than particles on galactic scales, creating interference patterns in dark matter distributions that might be observable through detailed studies of dwarf galaxies or through gravitational lensing. Primordial black holes themselves have been proposed as a form of dark matter, though surveys searching for these objects through gravitational lensing and other effects have constrained how much of dark matter can consist of primordial black holes in various mass ranges, and current limits suggest they can comprise at most a few % of total dark matter, unless they're in specific mass windows around 10 to 100 solar masses, where constraints are weakest. Dark energy, which drives the accelerated expansion of the universe and comprises about 68% of total energy density, remains one of physics' greatest mysteries, with no consensus explanation for what it actually is or why it has the strength it does. Most cosmological models treat dark energy as Einstein's cosmological constant, with unchanging energy density, but JWST observations that challenge the timeline of cosmic expansion could point toward dark energy evolving over time rather than remaining constant. If dark energy was weaker in the past and became stronger recently, as some theoretical models propose, That would affect when and how structures formed and potentially help explain why early structure formation appears more vigorous than standard models predict, because weaker dark energy in the early universe would mean stronger gravity's relative effect, allowing structures to assemble more rapidly before dark energy's repulsive effect became dominant. Self-interacting dark matter models where particles scatter off each other beyond pure gravitational interactions have been proposed to explain various puzzles in small-scale structure, including why dwarf galaxy centers appear less dense than pure cold dark matter predicts. And JWST's findings add another potential motivation for considering such models, since they can accelerate black hole formation in the early universe. If future observations confirm predictions of these models, including the presence of intermediate mass black holes in dwarf galaxies, it would suggest dark matter is more complex than the simplest cold dark matter scenario, and might involve new particle physics beyond the standard model. Dark energy, which drives the accelerated expansion of the universe and comprises about 68% of total energy density, remains one of physics' greatest mysteries, with no consensus explanation for what it actually is or why it has the strength it does. Most cosmological models treat dark energy as Einstein's cosmological constant with unchanging energy density, but JWST observations that challenge the timeline of cosmic expansion could point toward dark energy evolving over time rather than remaining constant. If dark energy was weaker in the past and became stronger recently, as some theoretical models propose, that would affect when and how structures formed and potentially help explain why early structure formation appears more vigorous than standard models predict. Testing whether dark energy evolves requires precise measurements of cosmic expansion at different epochs, which means observing supernovae and other distance indicators across a range of redshifts. And current data shows some hints of tension between different expansion rate measurements, but not yet conclusive evidence for evolving dark energy. JWST's ability to observe distant supernovae and characterize galaxy properties at high redshifts will contribute to refining these measurements, potentially revealing whether the acceleration of expansion has remained constant or has changed in measurable ways over billions of years. The fate of the universe depends critically on the nature of dark energy, because if it's truly a cosmological constant, the universe will expand forever at an accelerating rate, with galaxies eventually receding beyond our cosmic horizon and the universe becoming increasingly cold and empty. If instead dark energy weakens over time or even changes sign from repulsive to attractive, the expansion could slow or reverse, potentially leading to a big crunch where everything collapses back together. Understanding what dark energy is and how it behaves therefore connects directly to questions about the ultimate future of everything that exists. Our understanding of cosmic inflation, the hypothetical period of exponential expansion in the first tiny fraction of a second after the Big Bang that created the initial density fluctuations leading to all structure, also faces scrutiny from JWST observations. Inflationary models predict specific patterns in the amplitude and distribution of density fluctuations across different size scales, and if observed structure deviates significantly from these predictions, it could indicate either that inflation worked differently than standard models assume, or that some other mechanism created the initial fluctuations. Some researchers have suggested that if structure formation is more vigorous than predicted, perhaps inflation produced more power on large scales than simple models allow. But changing inflation this way often creates problems elsewhere by affecting predictions for the cosmic microwave background that are otherwise very successful. The discovery of potentially primordial black holes in the early universe, if confirmed, would have profound implications for understanding the very first moments after the Big Bang, because these objects form only under special conditions involving extreme density fluctuations or phase transitions in the first fraction of a second. Stephen Hawking originally proposed primordial black holes as a way to test quantum gravity effects, since small primordial black holes should evaporate through Hawking radiation and could potentially be detected through their evaporation, though decades of searches have not found convincing evidence. If massive primordial black holes seeded supermassive black hole growth, as some models suggest, it would mean the universe contained much more structure at very early times than previously thought. For our own place in cosmic history, the realization that the first galaxies formed so rapidly and efficiently raises questions about how typical or atypical our galaxy's formation was, because the Milky Way and its satellite galaxies like the Large and Small Magellanic Clouds represent relatively recent structures in cosmic terms, forming over billions of years through mergers and gradual accretion. If many galaxies in the early universe assemble their mass quickly in vigorous starbursts during the first billion years, the Milky Way's more leisurely formation might represent an unusual path, or alternatively, the early rapid formation might have been followed by quieter periods where not much additional mass was added. Understanding how galaxies transition from the vigorous star-forming systems JWST observes at high redshift to the more quiescent galaxies common in the local universe requires following their evolution over billions of years, and JWST's observations span cosmic time from the earliest epochs to relatively recent times, allowing astronomers to trace how galaxy populations change. Initial results suggest many early galaxies experience intense bursts of star formation that quickly exhaust their gas supplies, after which they become dormant red and dead systems, while other galaxies maintain more steady star formation rates over longer periods. The balance between these different evolutionary paths determines the mix of galaxy types we observe today. For the search for life in the universe, the early formation of massive galaxies and supermassive black holes means habitable environments potentially existed much earlier in cosmic history than previously thought, because planets require heavy elements created by stars, and those elements weren't abundant until several generations of stars had lived and died. If chemical enrichment happened faster in the early universe, with monster stars rapidly creating and dispersing heavy elements, terrestrial planets could have formed earlier than traditional models predict. However, the intense radiation from active star formation and black hole accretion in early galaxies might have made those environments hostile to life despite having the necessary ingredients, creating a window where planets existed but intense radiation prevented biological complexity from developing. The ultimate question raised by JWST's discoveries is whether we're witnessing a revolution in cosmology comparable to the shift from the steady-state theory to the Big Bang, or from a static universe to an expanding one, or whether we're seeing the final refinements to an essentially correct framework as remaining details get worked out through better observations and more sophisticated modelling. The history of science suggests major revolutions are rare and usually require overwhelming evidence that accumulates over decades before the scientific consensus shifts. But that same history also shows that when revolutions do occur, they often start with exactly the kind of observations JWST is producing. Anomalies that don't fit cleanly into existing theory and force scientists to question assumptions they'd taken for granted. Where all this leads depends critically on what JWST observes as it continues operations over the coming years, because the discoveries described here come from just the first few years of what's expected to be at least a decade-long mission, and follow-up observations will either confirm the most extreme early galaxies and black holes are genuine, or reveal their measurement errors and misidentifications. The telescope's ability to obtain deep spectroscopy of faint distant objects allows astronomers to definitively measure redshifts and characterize galaxy properties in ways impossible with photometry alone, and as more objects receive spectroscopic confirmation, the statistical case for or against standard cosmology will become clearer. Several key observations would help resolve current controversies, including detecting galaxies or galaxy candidates at redshifts beyond 15, pushing into the first 200 million years after the Big Bang, because if well-formed galaxies extend all the way back to that era, it would strengthen the case for fundamental problems with structure formation models. Conversely, if there's a boundary beyond which galaxies become noticeably smaller and less mature, that would indicate the extreme objects at redshift 10 to 14 represent rare but not impossible fluctuations. Finding evidence of population 3 stars through their unique chemical signatures would constrain models of the first stellar generation and help explain how chemical enrichment proceeded so rapidly in some early galaxies. The JWST mission has been allocated observing time through a competitive proposal process, where astronomers worldwide submit detailed plans for observations they want to conduct, and review panels evaluate these proposals based on scientific merit and technical feasibility. Cycle 4 observations beginning in 2025 include programs specifically designed to address questions raised by early JWST discoveries, with teams planning ultra-deep imaging to search for galaxies at redshifts 15 to 20, spectroscopic surveys to confirm distances and measure properties of hundreds of early galaxy candidates, and targeted observations of little red dots and other mysterious objects to determine their nature definitively. One particularly ambitious program will conduct the deepest JWST observations yet obtained, staring at a single patch of sky for hundreds of hours to reach sensitivities that will detect even fainter and more distant objects than previous surveys have revealed. And this ultra-deep field will provide critical data on whether the abundance of early galaxies continues increasing to earlier times or levels off, which would help distinguish between different theoretical explanations for the discoveries. Another program will use JWST's mid-infrared instrument to observe early galaxies at wavelengths, where dust emission and old stars are most prominent, complementing the near-infrared observations that dominate current surveys and allowing better separation of stellar populations to determine which galaxies are truly as massive as they appear. Ground-based observations will complement JWST's capabilities by providing different perspectives and capabilities, with the Atacama Large Millimeter Array Radio Telescope able to detect molecular gas and dust in distant galaxies, revealing the fuel available for star formation and constraining how efficiently early galaxies converted gas into stars. The 30-meter telescope, an extremely large telescope, currently under construction, will provide higher angular resolution than JWST through their enormous mirrors combined with adaptive optic systems that correct for atmospheric distortion, allowing detailed imaging of internal structure in high redshift galaxies to see whether they contain disk-like rotation patterns or chaotic morphologies indicative of mergers and violent dynamics. Several key observations would help resolve current controversies, including detecting galaxies or galaxy candidates at redshifts beyond 15 pushing into the first 200 million years after the Big Bang, because if well-formed galaxies extend all the way back to that era, it would strengthen the case for fundamental problems with structure formation models. Conversely, if there's a boundary beyond which galaxies become noticeably smaller and less mature, that would indicate the extreme objects at redshift 10 to 14 represent rare but not impossible fluctuations. Finding evidence of population 3 stars through their unique chemical signatures would constrain models of the first stellar generation and help explain how chemical enrichment proceeded so rapidly in some early galaxies. Observations of little red dots and other mysterious compact objects will clarify whether they represent new classes of systems not predicted by theory, or whether they fit within the extended range of known galaxy and black hole properties once properly understood. Spectroscopy is already resolving some of these mysteries by revealing many little red dots contain actively accreting black holes, though questions remain about why they're so common and compact. Following up early galaxies at longer wavelengths with JWST's mid-infrared instrument, or with ground-based telescopes, could reveal whether their stellar masses are truly as large as they appear, or whether bright young stars dominate the light, creating an illusion of greater mass. The next generation of telescopes coming online over the next decade will complement JWST by probing different aspects of the early universe, with ground-based extremely large telescopes like the Extremely Large Telescope and the 30-meter telescope providing higher resolution observations of specific objects, while future space missions might focus on wavelengths JWST can't access or push to even greater sensitivities. Radio telescopes are attempting to detect the 21-centimeter line from neutral hydrogen in the cosmic dark ages before the first stars formed, which would provide a completely independent probe of structure formation and potentially reveal whether the conditions leading to rapid galaxy formation were in place even before stars began shining. For now, the scientific community finds itself in a state of productive tension, where observations have outpaced theory, and everyone is scrambling to develop models that can explain what JWST is revealing. This is exactly the situation that drives science forward, because comfortable confirmation of expectations doesn't push understanding into new territory. Only surprises and anomalies force researchers to think differently and consider possibilities they'd previously dismissed. Whether the resolution involves modified dark matter, evolving dark energy, primordial black holes, an older universe, more efficient star formation, or some combination of all these factors remains to be determined. What's certain is that our view of the early universe has been fundamentally transformed by JWST in just 3 years, and the telescope is still only beginning to explore its full potential for deep field observations, spectroscopy, and time domain studies. The first galaxies are no longer theoretical constructs inferred from models, but observed realities we can study in detail, and those realities are forcing cosmologists to confront the possibility that the first billion years of cosmic history were far more dynamic, violent, and efficient at building structure than anyone imagined. The infant universe appears to have been remarkably precocious, developing complexity and structure on timescales that challenge our understanding of how gravity, matter, wand, and energy work on cosmic scales. Standing back from the technical details and astronomical jargon, what JWST has revealed is nothing less than a universe that refuses to behave as expected, and the implications of that refusal touch everything we think we know about cosmic origins. The telescope was built to look at the first galaxies and test our theories about how they formed, and in a sense it's succeeding spectacularly by revealing that those theories are inadequate, forcing scientists to either modify physics or accept that we live in an extraordinarily unusual part of cosmic history. The sheer abundance of discoveries that shouldn't exist according to standard models has created a crisis in cosmology not seen since the late 1990s, when astronomers first realized the universe's expansion is accelerating. That earlier crisis led to the introduction of dark energy into cosmological models, fundamentally changing our picture of what the universe contains and where it's heading. And it's possible the current crisis will lead to equally profound revisions in our understanding. Whether those revisions involve accepting that black holes formed before galaxies, or recognizing that primordial black holes seeded all later structure, or doubling the universe's age, or modifying how gravity works, the outcome will reshape humanity's conception of cosmic history. We may be witnessing the discovery that the first several hundred million years after the Big Bang were nothing like we imagined, with processes operating under extreme conditions that have no analogue in the later, more settled universe. The historical context for this moment in cosmology is worth considering, because science has experienced similar upheavals before, when observations contradicted established theory, and understanding how those earlier revolutions unfolded provides perspective on what might happen next. When Edwin Hubble discovered in the 1920s that galaxies are receding from us, with velocities proportional to their distances, it overturned the prevailing view that the universe was static and eternal, forcing Einstein to abandon his cosmological constant, which he'd introduced specifically to prevent his equations from predicting expansion. The discovery of the cosmic microwave background in 1965 settled decades of debate between Big Bang and steady-state cosmologies by providing direct evidence that the universe had a hot, dense origin, and the theory that had seemed most elegant and philosophically appealing to some cosmologists had to be abandoned in favour of the one supported by observations. The 1990s discovery of cosmic acceleration through supernova observations represents perhaps the closest parallel to the current situation, because those results also seemed impossible according to prevailing theory and required introducing a completely new component, dark energy, to explain them. The initial reaction was skepticism and suspicion of systematic errors, with many astronomers believing the supernova observations must be wrong or misinterpreted because the universe shouldn't be accelerating. Only after independent teams confirmed the results using different samples and methods did the community accept that something genuinely unexpected was happening. And even today, dark energy remains poorly understood despite being incorporated into the standard cosmological model. JWST's discoveries may be following a similar trajectory, starting with surprise and skepticism, moving toward acceptance that the observations are real, and ultimately requiring new theoretical frameworks to explain them, though whether those frameworks involve minor adjustments to existing models or radical departures from established physics remains to be determined. The difference between the current situation and past revolutions is that we now have far more observational data from multiple independent sources, constraining cosmic evolution, making it harder to dramatically revise models without breaking agreement with other well-established observations, which is why researchers are being cautious about claiming cosmology is broken, and why many favour astrophysical explanations over cosmological ones. That earlier crisis led to the introduction of dark energy into cosmological models, fundamentally changing our picture of what the universe contains and where it's heading, and it's possible the current crisis will lead to equally profound revisions in our understanding. Whether those revisions involve accepting that black holes formed before galaxies, or recognizing that primordial black holes seeded all later structure, or doubling the universe's age, or modifying how gravity works, the outcome will reshape humanity's conception of cosmic history. We may be witnessing the discovery that the first several hundred million years after the Big Bang were nothing like we imagined, with processes operating under extreme conditions that have no analogue in the later, more settled universe. The discoveries also highlight how much we still don't know, despite a century of progress in cosmology, because prior to JWST, the first billion years of cosmic history remained largely mysterious, with only indirect evidence and theoretical models guiding our picture of what happened. Now that we can directly observe that era, we're finding our models were wrong, or at minimum incomplete, and the humbling realization is that some of the most basic questions about cosmic origins remain unanswered. How did the first stars form? When did the first galaxies appear? How did supermassive black holes grow so rapidly? What ended the cosmic dark ages and reionized the universe? These foundational questions have no certain answers despite decades of research. What makes this moment in astronomy so exciting is the combination of revolutionary observations forcing theoretical innovation and the availability of tools to test competing ideas through further observations, meaning we're not stuck with untestable speculation, but can make predictions and check them against data. The next few years will likely see intense activity as researchers propose models to explain JWST observations, and then use those same observations plus new data to rule out ideas that don't work, progressively narrowing the range of viable explanations until a new consensus emerges. That process is already underway, with some ideas like purely photometric errors being largely ruled out, while others like self-interacting, dark matter, or primordial black hole seeds gaining support from confirming observations. For the broader public, the lesson from JWST's discoveries is that the universe continually surprises us and refuses to fit neatly into our expectations, which is both humbling and exhilarating because it means there's still so much to discover. The fact that a single telescope launched in 2021 could within 3 years find evidence that potentially overturns established cosmology demonstrates how much frontier science remains possible even in fields like cosmology that sometimes seem mature and settled. Every answer JWST provides raises new questions, and the telescope is revealing a cosmos far stranger and more interesting than the one we thought we knew. With impossible galaxies, inexplicable black holes, and chemical signatures that shouldn't exist conspiring to tell us the story of cosmic dawn is far from settled. The discoveries also remind us that our understanding of the universe is always provisional, built on the best available evidence, and subject to revision when better evidence appears, and JWST is providing precisely that better evidence across dozens of different aspects of early cosmic history. The standard model of cosmology has been incredibly successful and won't be abandoned lightly, but science has no sacred cows, and if observations demand new physics or new frameworks, the scientific community will eventually adapt no matter how uncomfortable the implications. That's the essence of the scientific method, following evidence wherever it leads, even when it leads somewhere unexpected. The philosophical implications of these discoveries extend beyond technical cosmology into questions about humanity's place in the universe and our ability to comprehend cosmic reality. Because if the first billion years of cosmic history were fundamentally different than we imagined, it raises questions about how well we can ever understand epochs and environments so removed from our own experience. We live in a mature, relatively quiet universe where galaxies evolve slowly, stars form at modest rates, and the cosmic environment is predictable and stable over timescales of billions of years. The universe JWST reveals at cosmic dawn was violent dynamics and apparently far more efficient at building structure than anything we observe today, suggesting the rules governing cosmic evolution changed dramatically between then and now. This realization challenges the assumption that physics is universal and unchanging across time and space, an assumption so fundamental to science that questioning it feels almost heretical. But if the early universe operated under conditions so extreme that qualitatively different processes dominated, we may need to accept that our local physics provides an incomplete guide to understanding cosmic origins. Alternatively, perhaps the disconnect between theory and observation indicates not that physics changed, but that we've been extrapolating too confidently from local conditions to early epochs, without fully appreciating how sensitive structure formation is to initial conditions and environmental factors that might have been very different when the universe was young. The human dimension of these discoveries shouldn't be overlooked, because the thousands of astronomers worldwide working with JWST data are experiencing something rare in science: the opportunity to make genuinely surprising discoveries that challenge established frameworks and force re-evaluation of fundamental questions. Many researchers have spent entire careers studying galaxy formation based on models that JWST observations now call into question, and adapting to this new reality requires intellectual flexibility and willingness to consider ideas that seemed unlikely or unnecessary before the observations arrived. The excitement and intellectual ferment in the astronomical community right now reflects both the thrill of discovery and the anxiety of uncertainty, as people grapple with data that doesn't fit expectations and search for explanations that preserve what works while accommodating what's new. Graduate students and early career researchers entering astronomy today have the opportunity to help solve these mysteries and potentially participate in a paradigm shift comparable to earlier revolutions in cosmology, making this an especially exciting time to work in the field despite, or perhaps because of, the confusion and controversy surrounding JWST discoveries. The questions being asked now about black hole formation, galaxy assembly, chemical enrichment and cosmic timelines are exactly the kinds of fundamental questions that drive scientific progress by forcing deeper understanding of underlying physical processes and connections between different phenomena. The technological achievement represented by JWST itself deserves recognition as part of this story, because the telescope's discoveries depend entirely on engineering excellence and decades of development work that pushed infrared detector technology, telescope design, and spacecraft systems to unprecedented levels of performance. The fact that a machine built by humans can observe galaxies from 280 million years after the Big Bang, resolve their internal structures, measure their chemical compositions, and detect black holes across cosmic time represents an extraordinary testament to human ingenuity and capability. The telescope cost about $10 billion and required contributions from thousands of engineers, scientists, and technicians across multiple countries over a development period spanning nearly 3 decades. And while that investment was controversial at times, the scientific return has exceeded even optimistic expectations. Looking forward beyond JWST's mission lifetime, future space telescopes are already being planned that will push even further into the infrared and potentially detect the very first stars and galaxies that formed in the universe, objects that may remain just beyond JWST's reach. NASA's proposed Habitable Worlds Observatory would have capabilities for imaging exoplanets, but also for deep cosmological studies, while more specialized missions might focus specifically on early universe science with designs optimized for detecting extremely faint and distant objects. Ground-based telescopes continue improving as well, with the next generation of extremely large telescopes entering operation in the early 2030s and providing complementary capabilities to space-based observations. The synergy between different observational approaches, space-based and ground-based, optical and infrared and radio and X-ray, creates a comprehensive view of cosmic evolution that no single facility could provide alone. And resolving the questions JWST has raised will require this multi-wavelength, multi-facility approach, combining observations, theoretical modeling, and numerical simulations in an iterative process of hypothesis testing and refinement. The scientific method at its best involves this kind of collaborative effort, where observations constrain theory, theory makes predictions for new observations, and the cycle continues until understanding converges on truth, or at least on models that accurately describe observations and make testable predictions. As we look toward the future of cosmology post-JWST, the field faces both challenges and opportunities unprecedented in its history. The challenges come from needing to explain observations that don't fit established theory, requiring either new physics or dramatic revisions to models scientists spent decades developing and testing. The opportunities come from having direct access to cosmic dawn through JWST's observations, allowing us to test ideas about the first galaxies in ways that were impossible, when theoretical models had no observations to constrain them. Additional data from radio telescopes detecting neutral hydrogen, from X-ray observations characterizing black hole growth, and from gravitational wave detections potentially revealing primordial black hole mergers will combine with JWST observations to provide a multi-messenger view of the early universe. Whatever the final explanation turns out to be, whether conventional astrophysics pushed to extremes or revolutionary new cosmology, the journey toward that explanation promises to transform our understanding of where everything came from and how the universe evolved from a hot, dense state into the vast, complex cosmos we observe today. The impossible galaxies JWST discovered may ultimately prove not to be impossible at all, but simply the signatures of processes we hadn't imagined, operating under conditions we hadn't anticipated, during an epoch whose physics we're only now beginning to understand. The universe is teaching us humility by showing us how little we knew about its earliest moments, and it's rewarding our curiosity by revealing wonders that exceed our theoretical expectations. The story of these discoveries is still being written, with new observations arriving monthly that either confirm or challenge preliminary findings, and the scientific literature is filling with papers proposing explanations, testing hypotheses, and arguing over interpretations. This is science at its most vibrant, a field in flux, as researchers grapple with data that refuses to fit neatly into existing frameworks, and out of this chaos will eventually emerge a clearer picture of cosmic dawn grounded in observations rather than speculation. Whether that picture looks more like an extended version of standard cosmology, with some parameters adjusted, or whether it requires fundamental reconceptualization of how structure forms in the universe, remains to be seen. For the general public watching these developments unfold, the lesson is that science remains a living dynamic enterprise where fundamental questions remain unanswered and where even well-established theories remain subject to revision when new evidence demands it. The popular conception of science as a body of fixed facts handed down by authorities misses the essence of scientific practice, which is a process of constant questioning, testing, and refinement driven by observations and constrained by logic and evidence. JWST's discoveries show that process in action, with astronomers around the world working to make sense of data that challenges expectations and forces reconsideration of ideas that seemed settled. The fact that we can even ask these questions and make these observations represents progress compared to earlier eras when cosmology was purely philosophical speculation unsupported by data, and the fact that we're finding answers different than expected is ultimately more exciting than confirming predictions would have been, because unexpected discoveries open new research directions and reveal aspects of nature we didn't know existed. The universe is under no obligation to conform to our theories, and when it doesn't, we have the opportunity to learn something genuinely new about how reality works at scales and conditions far removed from everyday experience. For now, the James Webb Space Telescope continues its mission of peering back to the beginning of time, finding galaxies that formed when the universe was just learning to make stars, revealing black holes that grew impossibly large, impossibly fast, and detecting chemical signatures that tell stories of stellar populations that evolved before they should have existed. Each discovery adds another piece to the puzzle, and while we don't yet see the complete picture, we know it's a picture of a universe far more dynamic and complex in its youth than we ever imagined. The cosmos refuses to be simple, refuses to conform to our expectations, and in doing so reveals depths of mystery that make the scientific enterprise all the more thrilling and essential. If you found this deep dive into the edge of cosmic knowledge fascinating, do me a favour and hit that like button. It helps the channel reach more people who want to understand the cutting edge of space science. Subscribe if you want more explorations of astronomy's greatest mysteries, because we're living through a golden age of discovery where telescopes are revealing truths about the universe that challenge everything we thought we knew. And there's never been a better time to follow along as humanity rewrites the story of cosmic origins. The James Webb Space Telescope has only scratched the surface of what it will ultimately reveal, and the discoveries yet to come promise to be even more revolutionary than what we've seen so far, because each observation pushes deeper into cosmic time toward that first moment when the universe ignited with starlight and began its journey from darkness to the spectacular cosmos we call home. Thanks for watching. Keep looking up because the universe is stranger and more wonderful than we ever dared to dream.